Hello, my dear students. Hope you are in good health and spirits. So, in this today's lecture, we will discuss about the Grand Canonical Ensemble, and we will drive the derivation of a system which is present in this Grand Canonical Ensemble, and then what will be the partition function of that system, and from that we will find out the various thermodynamic statistics. And what is their physical significance that we will discuss in this lecture. So let us start. So till now we have discussed microcanonical and canonical ensemble, and the change from microcanonical to canonical was because of the reasons which are related to how we define the ensemble as in microcanonical. So we have discussed that the n, v and e, so they are constant, so in microcanonical ensemble. And then we give reason that it was not easy to measure the total energy, which shouldn't change according to microcanonical ensemble, because we cannot restrict this particular energy for the fixed value. From this microcanonical ensemble, we formulate the canonical ensemble theory, and in this we have discussed that the n, v, and t. So these three macrostates we have kept constant, and energy it could be shared among the systems which are present in this ensemble. So energy is shared. So this is the major difference between this microcanonical and canonical ensemble. And now we know that n is also a measurable quantity. So in practice, like energy in canonical one, so we formulate now the theory of a grand canonical ensemble, in which the number of particle and E, so that can be exchanged among the various systems in the ensemble. So we regard that system, so in which both n and v, so it can be n and e, it can be variables, so which can be changed from one system to another system. So that ensemble in which both the number of particle and the energy which is being shared among the systems which are present in the ensemble, that ensemble is generally known as the microcanonical ensemble. So in this case we will kept these three parameters, mu, which is related with the change in number from one system to another system, and that is generally known as the chemical potential. So these three parameters which will be fixed for this grand canonical ensemble, while the n and v variables they are being shared among all these systems. So the procedure for studying the statistics of these variables n and e, so it is we can do it by two ways. So first we can consider the given system which is immersed in a large reservoir, so like we have discussed in the canonical ensemble, and from that which we can find out the exchange in energy and n value which is being exchanged between the system and the reservoir. So the second, we can consider a member of what we call a grand canonical ensemble, which consists of a large number of mental copies. Suppose this is our ensemble, and there are quite identical systems which are present in this grand canonical ensemble, and the value of this n and e, so it is being shared among all those systems. So the value of this n and e, so it is being variable. So we will choose this first conditions by keeping the systems which is present in the heat reservoir. So let us discuss and try to find the equilibrium relation between a system and the reservoir. Now consider we have a large heat reservoir and the system which is being immersed in this heat reservoir, so we call this system as A and this heat reservoir as A dash, and at the equilibrium condition volume V and temperature T and chemical potential mu, they are fixed, like N and E changes but total number of this energy, so like the N naught value, so which is the value of Nr for the system plus the number of particles within the heat reservoir, so this value is always conserved. So similarly the total energy of this as whole system and reservoir, it is always constant. So ER, that is representing the energy of system, and ER dash at the same time the energy of this heat reservoir. So these are some of the conditions so which we will apply. So from that, so let us say we can say this is our equation number 1, this is equation number 2, and clearly you can see that from 1 I can write it as Nr over N naught, which is equal to 1 minus Nr dash over N naught, so which is very less as compared to 1, because the heat reservoir, it is having a very large value as compared to system. So similarly you can formulate the, so energy we will represent with S, so the particle here Nr, and energy we represent with S, so in order to avoid confusion. So similarly, so this Nr dash and Es dash, so Es over E naught, so which is 1 minus Es dash over E naught, which is very less as compared to 1. So these 1 to 4 conditions, so they are at the equilibrium point when the energy and the N for this heat reservoir and this system, so they are in the state of equilibrium. So from that we will find the probability PR S, which will depend upon both the value of N and E. So that means at any time t, the system A is found to be in a state, so which is Nr and Es state, and it is directly proportional to number of microstates, so which is dependent upon the number and energy of this heat reservoir. So the reservoir can have for the corresponding values Nr dash and Es dash. So when the system which is having these particular values, so the probability at a particular instant of time t, so it is equal to the number of microstates, so which is equal to Nr dash Es dash. So this we can write down as omega dash N naught minus Nr E naught minus Es. Now taking the log of this equation, so if we will solve this omega value, and from that we can find out the probability distribution. So taking the log of omega dash, so what we get is log of omega dash, which is equal to N naught minus Nr E naught minus of Es. So taking the Taylor expansion of this, so this equation will, we can write as omega dash E naught N naught plus curly log of omega dash over curly of N dash. So at the most probable state, so N dash will be equal to N naught, because the value of ns, it is very less as compared to ns dash. So then we will take minus of nr plus curly log of omega dash over curly e dash. So this Taylor expansion we have done when we have solved this for the canonical ensemble. So you can check those notes how we can expand this equation using the Taylor expansion. So this equation becomes log of omega dash n naught E naught minus of nr. So this Bractor term, so it is a function of number of particles which are being changing. So this we can write out as a xi value, you can say minus of es and this curly log of curly e that we have derived, which is equal to beta. So this equation we can write down as log of omega dash n naught E naught minus of nr, and this change in number or change in microstates with the change in number, so that we generally represent it as minus mu over kt. So where mu is the chemical potential, so which is being changed with the change in number of particles. So this equation comes out to be log of omega dash plus nr mu dash over kt dash minus of es over kt dash. So let us say this is our equation number 6. So the mu dash, T dash, they are the representative chemical potential and the temperature of the heat reservoir. So putting the value of this mu, so we know that this is equal to alpha minus mu over kt, and similarly beta value we know it is equal to 1 over kt. So when we put these values in equation number 6, so our equation becomes log of omega dash nr dash es dash, so that is equal to log of omega dash n naught E naught minus of alpha into nr minus of beta into es. So this term, that is the probability, so which is dependent upon these two component r and s, so which are being changing with respect to n value and e value. So this equation we can write down as, so this is exponential of, we can write this equation as, if we take the exponential of this term, so this equation becomes omega dash n naught E naught exponential of minus alpha nr exponential of minus beta into es. So this PRS, so that is equal to omega dash into n naught E naught exponential of minus alpha into nr minus of beta into es. So this is the same equation which we have derived for the canonical ensemble. So except one, this addition term, now we have found this term extra. So due to the change in number of particles between these systems and heat reservoir. So this equation we can write as, which is equal to a constant c exponential of alpha nr minus of beta es, because this value, so that we have generally considered as a constant for the composite system, and from this we can evaluate the value of c. So the maximum value of this probability PRS, so it is equal to 1. So this P is c into exponential of alpha nr minus of beta es, and from that we can find the value of this constant. so which is the inverse of exponential of alpha into nr minus beta into es. So our probability density equation comes out to be exponential of alpha nr minus of beta into es over summation of exponential of alpha nr minus of beta into es. So this denominator term, so that is generally considered as the partition function for this grand canonical ensemble. Now let us drive out the physical significance of these various statistical quantities for this grand canonical ensemble. So what is the significance of each term which is present in this equation? So let us say this is our equation number 7. So we know that the expectation value of this n, so this equation, that is a summation of nr exponential of minus of alpha into nr minus of beta into es over summation of exponential of alpha into nr minus beta into es. So this equation we can also write it as minus curly over curly alpha log of summation of this denominator value alpha nr minus of beta es. So similarly we can find out the expectation value of this energy, so that is generally the average energy of system. So this similarly we can write it as er exponential of alpha nr minus of beta into es over the partition function exponential of minus alpha nr into beta es. So this we can again write it by taking the derivative with respect to beta. So we get log of summation exponential of alpha nr minus of beta into es. So these two are important equations which will help us to establish the connection between this statistics and thermodynamics of the system which is present in the grand canonical ensemble. So let us say this is equation number 8 and this is equation number 9. So again we will introduce a quantity or a undefined parameter, so which is dependent upon these two value of nr and es. So we will follow the same approach which we have used for the canonical ensemble. So introducing a physical parameter, let us say q, so which is log of summation of exponential of alpha into nr minus of beta into es. So this q, since it is dependent upon three parameter alpha, beta and es, so this is generally known as the q potential. Now taking so let us say this is equation number 10. Taking a differentiation of this q for all these three parameters, so we can write this equation 10 as derivative of q, it is 1 over derivative of log is, so this term comes in the denominator, minus of alpha nr minus of beta into es summation of minus of nr exponential of minus alpha nr minus of beta into es into d alpha plus summation of minus of es exponential of minus alpha nr minus of beta into es into d beta plus third summation of minus of beta exponential of alpha nr minus of beta into es into DES. So this we can write down as equal to minus of expectation value of n. So this first term you can check from this equation number 8. So this is equal to expectation value of n into d alpha. The second term, which is the expectation value of this uh, energy, so that is eigenvalue into d beta, and the third term, which is equal to beta into summation of, so this summation of exponential, so that is equal to NRS over the total number of systems which are present in this grand canonical ensemble into DAS. So this is the equation which we will get, and we can rewrite this equation as, so if we move these n and e parameter to the left hand side, so our equation becomes dq plus alpha into n bar plus beta into e bar, so that is beta into alpha over beta into d of uh, n plus expectation value of d into e minus of 1 into n summation of nrs into d into es. So this is the equation which we will get. So compare this equation 11 with the thermodynamics first law. So according to thermodynamics first law, it is the total heat, it is equal to dE plus curly by curly omega, so that is the work done by this system or on this system. And since there is a change in number between these systems, so we will introduce this minus of mu into dn bar. So here E bar, that is representing the expectation value of energy per system, and N bar, that is representing the expectation value of number of systems. Now compare this equation Q, so which we have introduced, and this equation 11. So if we compare these two equations, so let us say this is our equation number 12. Now comparing these 11 and 12, so we can see that the value of mu, that is uh, so this is with respect to dn, so this is equal to minus of alpha over b. So you can compare these two equations, and from that you can find out that, so the mu which is equal to minus of alpha beta, so similarly you can compare the change in work done, so that is equal to minus 1 over n summation of nrs into d into es. So this is the work done, which is always a change in this value dE of, so this dE, it is being compared with this value, and the term d omega, it is compared with this value. So these are the two equations. Let us say this is equation number 13 and this is equation number 14. So our equation becomes dq plus alpha into n bar plus beta into e bar, so that is equal to beta into delta q. So this we can write it as curly q over kt. So 1 over kt, we can write it curly q over t. So the right hand side of this equation, so that is curly q over which is equal to t into delta s. So this is generally we can write it as d of s. So this equation becomes dq plus alpha to expectation value of n plus beta into expectation value of E. So that is equal to S over K. So from this we can find out the value of this parameter which we have introduced, that is this Q potential. So this Q, it comes out to be, so since we have removed these derivative terms, so we will remove this derivative expression. So Q comes out to be S over K minus of alpha into expectation value of n minus of beta into expectation value of E. So putting the value of this alpha and beta, so this equation becomes alpha is minus mu over kt, so we can write it as mu over kt into n minus e over kt. So from this we can find out the q, it comes out to be ts plus mu into n minus of e over kt. Now we know that the Gibbs free energy, it is equal to mu into n bar. So this is the same which we have found. So this Q value we can write it as Ts plus Gibbs free energy minus of E over kT. So which is equal to, so Q comes equal to PV over kT. So this is our undefined parameter, that is the Q potential. So it comes out to be equal to PV over KT. So PV is that is the change in work done, so which is dependent upon this temperature, how it is being exchanged. So this equation, it will provides the essentials relation between this thermodynamics and the various states of this grand canonical ensemble. Now to derive the further results from this equation, so Q which is equal to P over KT. So we will introduce a new parameter, that is Z. So Z which is equal to exponential of minus alpha, so which is exponential of mu over KT. So this Z is called the Fugicity of the system. So Fugicity is generally defined as the escapability of the particles. So that is the tendency of a particle to prefer one phase over the another. So this is generally represented as the escape capacity of the particle. So that is the tendency of particle to prefer one phase over the other. So depending upon the what are the parameters for that phase, for example, the particle will be present in a phase of low fusicity. So it means where the escapability is least. So particle will always tend to follow towards that direction where the escapability is least. So this fugicity, it is analogous to this partial pressure when we apply the thermodynamics to any non-ideal gas for any component. So for ideal gases, this fugicity term, it is generally related with the partial pressure of the gases. So for the large system where the pressure, it is very high and changing quite frequently, then we will introduce this fugicity. So in this case, our Q potential, so the value of Q which we have introduced, log of summation of exponential of minus alpha into NR minus beta into ES. So this Q, it comes out to be, we can write it as summation of exponential of minus alpha, that is Z. So this is Z raised to power NR into exponential of minus beta into ES. So this Q potential, so which is equal to PV over KT, so that we can write it as log of summation of NR, which varies from 0 to infinity, ZR, Z raised to power NR into this exponential of summation of exponential of minus beta into ES. So this is the partition function for the canonical ensemble. So maybe if you remember, so this is the value of partition function for the canonical ensemble. So we can write it as QNR into VT. So this Q, which is we introduced a new parameter. So this is dependent upon this logarithmic value of Q1 ZVT. So this Q1 ZVT, so that is equal to, I will write it here. So Z, V and T, so this is dependent upon these three parameters, summation of NR from 0 to infinity, Z raised to power NR into Q of NR VT. So this Qn ZVT, that is the partition function of a grand canonical ensemble, and this Qn VT, that is the partition function of canonical ensemble. So this is actual relation between this partition function of a grand canonical ensemble versus the canonical ensemble. So once we find out the value of this partition function of a grand canonical ensemble, from that we can find out the various thermodynamic parameters like the pressure, the number of particles, the expectation value of E, and all other parameters. So that we will derive in our next lecture. So till then, goodbye. See you in the next lecture.